Okay, hi everyone. Today we're very happy to have Scott Hughes from MIT, who will tell us where do we go now. So please, Scott.
All right, well, thank you. I'm delighted to be here and to make this invitation work out right now. And so, my goal today is to tell you sort of what I've been thinking about in terms of we've had those of us who work in gravity theory, in particular those of us who work in gravitational wave physics. It's been a great decade. There's been a tremendous amount of theoretical promise that has really been delivered by the data that we are getting, but the story isn't over. As I said in a previous talk once, we've kind of reached the end of the beginning, and we now need to start thinking about, okay, where are the next paths that we're taking? And to illustrate some of the points that I want to make, I have a couple of parables that I like to go through. And so, oh dear, hang on a second. There we go. So my first parable is actually related to work that I did when I started my PhD. So I began studying as a member of Kip Thorne's research group in 1993. I was very excited. I had done an undergraduate class in general relativity, studied things related to black hole collisions, and I was really interested in the idea of taking some of that stuff, applying it to astrophysics, and maybe even making some measurements. And but at that time, if you looked at the literature of what people were thinking about in terms of gravitational wave measurements, everyone was focused on binary neutron stars. And there was a great reason for this. We knew binary neutron stars existed. We knew that there were tools, theoretical tools that we could use to model their waveforms. And thanks to calculations that have been done by many people, including I think some who are on this call, we had some confidence in what the event rate was. So binary neutron stars really was, if you look at the literature of the early 1990s, the bread and butter source that people thought about for gravitational wave measurements. But Kip Thorne suggested as one of my first thesis projects that we think about what you might be able to measure if nature produced binary black holes. And one of the things that I did in work with Anna Flanagan was demonstrated that the binary black hole waveform, even though it was poorly modeled, we could make some estimates as to what it would look like. And we found that it was perfectly aligned for the sensitivity of the early LIGO interferometers, but a lot of the best sensitivity lay in a region where analytic techniques for modeling the signal did not work well. And so when we wrote our paper in the late 1990s, this was really telling the numerical relativity community, we are going to need better models. We need to develop waveforms. Now, interestingly, at that time, we sort of, based on just what we were able to estimate for the signal strength and what the detectors were going to look like, Flanagan and I actually made a prediction in a paper in 1998 that binary black holes would probably be the first sources that LIGO Virgo would measure. But you may notice we made a very wishy-washy kind of prediction. They might very well be the first sources. And one reason that we kind of held back on a strong prediction was that a lot of our astronomer friends were saying, okay, your analyses are nice, but nature's not going to produce any binary black holes. I actually am presenting here, this is the last page from an article in a conference proceeding that was, this is the report of a talk that immediately followed. My colleague Anna Flanagan gave a talk on our model for the binary black hole waveform and how important it would be. And it was immediately followed by Lev Jungelson telling us there won't actually be any binary black hole mergers, which when you're a fifth-year graduate student starting to apply for postdoc positions is a little depressing to hear. So I began to wonder at that point whether my entire PhD thesis should just be multiplied by the number 0. Well, fortunately, I had a PhD supervisor who didn't worry so much. And in fact, he actually wrote on an early draft of our paper, I think you will regret not phrasing this prediction more strongly when LIGO is regularly measuring merging black holes in about 5 years. I love telling this little anecdote because it illustrates two things. One is Kip's optimism and confidence really is, I think, centered on a deep understanding of nature and of physics. But it also reflects a deep misunderstanding of how long it takes people to get things done. And so the idea that in 1996, we were 5 years away from measuring gravitational waves is very entertaining. That being said, the idea that we would be regularly measuring merging black holes turned out to be dead correct. Okay, and so the wisdom of the conventional community, it was already changing prior to LIGO's first detection, but then it got nailed down over an interval of zero point 0.2 seconds on the morning of 14th of September. And what is one thing that is exciting about this from the perspective of gravity theory is that in order to make the data that are being measured by the detectors match with what theory predicts, you need to have global space-time consistency. It's dynamic, it is strong field. There are no small parameters that go into this kind of an analysis. And so it is just an amazing sort of fit of a global prediction of general relativity to what is being measured. And this has been just, these kind of events just keep happening in keeping with Kip Thorne's statement. So at this point, there are 100 events that have been found, analyzed, and published. There are, I'm not officially a part of the LIGO team, but you can get an app on your phone that announces candidate events. I actually deleted it because I got tired of it going off all the time. But it generally goes off, every couple of days at this point. So binary black holes just keep happening. And most recently, the band in which we are measuring these things has gotten a lot wider. So by looking at long-term monitoring of radial pulsars, we have been able to determine that there is a pattern in the timing residuals from these very regular clocks that nature provides for us. And the pattern of the disturbance on the sky is, which is, it's correlated to how widely separated they are. It sketches the quadrupole pattern that is expected if there's a background of gravitational waves from the hum of many stochastically superposed sources. So we live in a universe that is rich with gravitational waves. The most plausible explanation for this one is that these are massive binary black holes orbiting with periods of years. So binary black holes in particular are just throughout the universe. And this has been, for me, as a gravity theorist and as somebody who thinks about the astrophysics of gravitational wave signals, it has made the past 10 years extremely exciting. So where do we go now? This is the topic of today's talk. So we've kind of had we would call in the US a gold rush of these first discoveries. I think about everyone running out west and sort of looking for gold in the fields of California before people moved in and started building housing everywhere. That's kind of where we are. We've mined all the easy to find gold. Everyone is setting up their various developments and housing projects. And I think we need to think a little bit more carefully to develop where we're going to be going forward. As a theorist, one of the things that's important to bear in mind is that the progress in this field is being driven by advances in the detectors. So I'm focusing here on the interferometers that are under development. LIGO is just the first stage in a development of detectors on the ground that are going to continue improving in sensitivity and in bandwidth. And we are going to be launching space-based detectors. So it's on the agenda of the European Space Agency now to launch in about 10 years a detector that would be sensitive to these waves at much lower frequencies, sort of periods on the order of minutes. As you lower the sensitivity, and I show here a sequence of ground-based detectors in my left-hand panel, you're getting more signal to noise for every cycle of wave that you are measuring. This gives you better opportunity to resolve the nature of the signal, to learn about the characteristics that come with that. As you move into different bands, band is the frequency band that you measure these things in, opens up sensitivity to different parts of the gravitational wave spectrum. In particular, you go to lower frequencies, you are sensitive to larger masses. And so what's particularly exciting for LISA is that this is expected to be sensitive to many signals arising from processes that involve the million solar mass black holes we find in the cores of galaxies. And indeed, a good chunk of my talk is going to talk about what we expect to, how we intend to model those signals. And then finally, bandwidth, especially with the ground-based detectors, we are developing instruments that will be wider band. When you have a wider band, the signal enters, you are sensitive to this signal starting at lower frequencies. And so you're able to measure more signals from it, more cycles from it rather, and give you much higher precision on what you measure for the gravitational waves properties. So we've already learned a lot, and you should, it's an important question as you begin planning the next generation of instruments to take stock in what you've learned so far, what you have not learned, and what you would like to get out of future measurements. And one thing I'd like to emphasize is that already with what we have, general relativity absolutely works. One can argue about whether there are details that need to be pinned down better, whether with very precise things we might be able to see evidence for additional fields or additional degrees of freedom that go beyond general relativity. But certainly, if you just take Einstein's general relativity and you devote your career to modeling gravitational waves with that, you're going to do fine. We've learned that the sources that instruments like LIGO and Virgo and Kagra are measuring come from a broad range of masses and mass ratios. So the black holes that have been measured range in mass from about 6 solar masses up to about 100. We've measured several neutron stars, and we've seen systems with mass ratios that range from roughly equal mass systems to fairly lopsided ones, about 9 to 1. I think actually it goes a little bit more extreme than that now. We see clear evidence that there is non-zero spin in these systems. However, spin is a very delicate parameter to measure via a gravitational signal. What we're looking for is the rather subtle way in which spin changes the gravitational interaction, modifies the orbits, hopefully causes precessions that we can attempt to measure. And with the kind of instruments we're measuring right now, we don't have that many cycles. And so even though we see evidence for non-zero spins, there's very broad posteriors when you do your analysis of this. It tends to be peaked away from zero, so we're confident the spin is there, but we can't say what its value is very precisely.
Can I ask a question?
Yeah.
So the events that are more towards extreme mass ratio, these 1 to 9s that you're talking about, are they better in terms of inferring spin?
That's a good question. I believe they are. I would have to go back and take a look to remind myself of that. But one of the main issues is that because the total number of cycles that are in band, it's a combination of mass and mass ratio that determines that. And so you do have more cycles in those cases. And so I would suspect that, I'll be blunt, I've not looked at the data on those carefully enough to answer your question as coherently as I would like to. I think one issue is that for some of them, the effect is still fairly subtle. And so, they're still relatively broad, but I think you're correct that they're not as broad as it is for sort of the one-to-one systems. Even in these cases, though, the spin orientations typically are not that well constrained. That tends to be information that comes from, to get really precise information about spin orientation, you need to sort of see some of the modulation effects that we expect from precession, and there's not enough signal in band to really pick that up. What is kind of interesting is we are already getting enough information now that there's an industry developing in the astrophysics community of using these kind of measurements to constrain the properties of the progenitors and to learn about the populations of stars that form these binaries. So what have we expect but we have not yet seen? So one thing, which I think is perhaps not that surprising, but it's something that we're nonetheless going to keep looking for, is we've seen no evidence in any of the systems so far of orbital eccentricity. Of course, we see tremendous orbital eccentricity with the binary pulsar systems, but eccentricity is bled away during the inspiral. So it's not that surprising that if you think about a binary pulsar system, by the time it enters the band of a LIGO type detector, it would be consistent with an eccentricity of 0. Nonetheless, you might expect that some of these systems form via capture processes fairly close to merger, and so they might have some residual eccentricity at the time of the merger. And indeed, there is one event where people have claimed that that's exactly what happened. This is a particularly massive system. It looks like the merger of a roughly 40 solar mass black hole with a 60 or 70 solar mass black hole. And the thought is that it might have been through dynamical processes and involved eccentricity. As I was saying in the previous one, we cannot state for certain that we have systems where the spins are strongly misaligned with the orbit geometry. It is not ruled out, but we cannot establish that definitively. And again, this one event appears to be a possible counterexample to that. And the issue here is that when one looks at the spectrum of gravitational waves at the very end, you have to include modes that can only be sourced if you have a very misaligned merger, misaligned coalescence going into this. I'm going to talk in a couple of slides later in my talk that there's a really cool bit of physics related to what we call tidal heating, essentially the gravitational transfer of angular momentum between spins in orbit. This must be present. I think this is going to be a huge source of interesting science with future LISA measurements, but we need more band, we need more cycles to see it now. And finally, these binaries don't exist in a vacuum. We have to have interactions with the environment, and those should have an effect on what we measure. All of these effects, as we are able to measure these things more precisely, we're going to need to model them more precisely, or else we're going to have systematic confusion in our measurement models. If we want to avoid confusing all these effects with each other, or with even other effects that were not listed on this thing here, we need good models to put all these things together. And so the job of the theorist will be to make these models and to understand how to avoid this confusion. And I would argue that as people who think about whether or not we are testing the nature of gravity itself, this is particularly important. Because if you do not understand the simple general relativity version of the waveforms, you cannot claim that you have seen any kind of an effect that goes beyond the structure of general relativity. Here's my second parable. There's a fascinating story that arose in an early version of the binary pulsar timing. So when the 11-year nanograv data set was released, or I should say before it was released, but when they were analyzing it, there was a residual in the data set. So ignore the heavy solid lines on my plot for just a second. Look at the lighter dashed lines. So that was the initial fit. What they found was that there was a signal in these data that was consistent with a gravitational wave being present. It was sort of on the high end of what people expected, but it was very exciting that it looked like already in the 11-year data set, they were seeing evidence for a stochastic background of gravitational waves. But when they looked at it more carefully, they found that the correlation among all the signal among all the different pulsars had the wrong shape to be a gravitational wave background. Okay, so you would expect it to be that dashed red line there. First of all, it's quite noisy. But when you look at what shape it does fit, the trend suggests a residual that is dipolar rather than quadrupolar. Now in gravity, if you have the wrong dipole moment, that means you have the wrong center of mass. And so what people realized was that they're making these measurements via radio telescopes on the surface of the Earth. They need to correct for the spin of the Earth around its axis, the motion of the Earth around the sun, the motion of the sun around the solar system barycenter. And so when they corrected that, they sort of allowed that to be a free parameter. They basically determined that we had the wrong value for the solar center barycenter. And indeed, when you allowed that to be fit by the data, the evidence, the strong evidence for a possible signal just disappeared. And what's really kind of cool here is at the end of the day, the solar system barycenter was off by about 100 meters. Now, bear in mind, this is essentially a weighted sum of mostly the mass of the sun and the mass of Jupiter on Jupiter's orbit. Okay, and one of the reasons why this showed up so strongly is that the 11-year cycle was close to a period of Jupiter's orbit. So they've now, there's a new NASA mission, the Juno mission, has given us better data on the solar system barycenter, so they don't need to fit for this, and that's part of what went into the 50-year thing. The parable, the lesson I want to take from this parable is you can be surprised by a systematic and come to the wrong conclusion very easily. So we really need to think these things through carefully. When we're modeling things like binary black hole systems, a major source of the challenge, as I like to say it, is general relativity doesn't actually have a two-body problem. It has a one space-time problem. We can start with initial data that clearly describes two widely separated black holes. We can evolve them forward in time, but then we need to determine the system's dynamics and the gravitational waves it produces from the dynamics of that space-time. That is a very challenging theoretical and computational problem, and I don't have time to describe it, but there's actually a wonderful piece of work that was developed by Kip Thorne and Jim Hartle. At this point, it's almost it's over 40 years ago. 42 years ago is when they put this paper out, which demonstrates that actually, even as a matter of principle, if you start with initial data of two bodies that are at finite separation from one another, you cannot even in principle define individually the masses and spins of those objects. Okay? You can do it when they're infinitely far apart from one another, but as they come close together, there is a built-in ambiguity because of the nonlinearity of the field equations. And we are actually starting to reach the point where some of the accuracy requirements that we would like to set, the kind of precision we're making, is hitting this sort of built-in ambiguity associated with the Einstein field equations. I find this difficult, and I want to try to do a problem that I know how to solve. And so I'm going to discuss for the remainder of this talk one particular limit, which is both of astrophysical interest and theoretical interest, the extreme mass ratio inspiral, so a capture of a stellar mass black hole onto a strong gravity orbit of a massive black hole. One reason why this is a really nice problem from the theory point of view is that when we set this up, the spacetime of the binary is dominated by the properties of the larger object, and we can model the effect of the smaller body using perturbation theory. This gives us a set of equations that we can solve very precisely. And we can use this to make long duration models, waveforms describing very long duration signals. These kind of events are actually explicitly listed as one of the main targets for the space-based laser interferometer space antenna, which ESA intends to launch sometime in the 2035 time frame. Even though individually per galaxy, such things should be rare, the gravitational waves should be heard out to about a redshift of 5. So these are likely to be quite plentiful in the LISA data. And something which is particularly exciting, and it's different from the last time I gave a talk on this, is that we may already be seeing this happening. There is substantial evidence from certain X-ray sources that we are seeing compact objects orbiting in these Emery type of orbits and interacting with an accretion flow. And there's a wonderful paper by Itai Lineal and Brian Metzger that lays out the phenomenology of this. And I'm going to talk a little bit more about the possibility of these sources towards the end of this talk. So, if I want to model these as a relativity theorist, there's 3 places where the small mass ratio of the system helps me out. First of all, I need to solve the field equations. But I'm going to treat the space-time that I'm solving for as the Kerr space-time. I'm going to describe the black hole as the exact Kerr solution, and then I'm going to make a series where the mass ratio controls perturbations to that space-time. We very accurately now understand how to solve things at first order in the mass ratio. So this has been a big chunk of my research. Quite a bit of the research of people who are students of Professor Ori, who's here on the call, have put a lot of time into this. And I'm happy to report that it's essentially, at first order, a solved problem. It's not an easy problem, but I think we have it completely under control. The second order analysis is also underway, and there are some good results for some interesting special cases, which I'll talk about in a couple slides. Once we have the space-time, we need to describe the motion, how the secondary moves in that space-time. And this really is it's the simplest thing. We're going to treat the motion as a geodesic of that space-time. And if I think of the motion as being close to a Kerr geodesic orbit, then I just get a force that pushes me away from that geodesic orbit, and I need to integrate up the effects of that force. Once that is done, I then just need to integrate up and construct the entire motion in order to make waveforms. So it's a pretty well-described recipe. So I'm going to get technical for just a moment here, because I want to describe what happens when we actually, so I'm not going to talk too much about how we solve for the space-time, but I want to talk about the motion, because there's important things that arise there. So the way we describe the motion is I'm going to introduce an action angle variable formalism. So these Q's, the Q variables, are kind of a generalized angle variable that describes the motion. So Q phi is essentially an axial angle. QR and Q theta are kind of like anomaly angles that are related to the motion in radius and the motion in the polar angle theta. These J's are conserved integrals describing the background motion. Okay, and so I'm just going to set up a system of equations where I expand things in this mass ratio epsilon. So let's look at this system of equations order by order. If I do it to 0th order in the mass ratio, these angle variables I've introduced just accumulate at a steady rate, and the integrals of the motion are conserved. This is nothing more than the motion of a geodesic of a black hole. This is a geodesic orbit of a black hole, sort of in weird language. What's interesting about this is that when I look at this for Kerr black holes, I get this tri-periodic structure. So as a body orbits a Kerr black hole, it is completely integrable, and we find that the motion is described as simple sort of sinusoidal orbits with a couple of precessions on top of them. And so I can describe those precessions by treating the motion as having a frequency associated with the radial motion, a frequency associated with the polar motion, and a frequency in the axial direction. And a lot of the interesting behavior that characterizes relativistic orbits can be regarded as just beating between those different frequencies. So to give an example, if I have, here's a little video showing what one of these orbits looks like. The sort of whirling that we see at small radius here That's nothing more than the periastron precessions, the same effect that causes Mercury to whirl a little bit of extra angle on its periapsis near the sun. And in the language that I've used here, this is given by sort of a beating between the axial frequency and the radial frequency. This orbit is also tilted, and there's an additional effect due to the precession of the orbital plane, but hopefully you get the idea here. So my individual orbits are described by a sequence of these frequencies. I then turn on these corrections that go beyond geodesic motion. To understand what's happening with them, I'm going to expand them in a Fourier series. When I expand them in a Fourier series, I find that there are certain terms that have an average value on an orbit that is constant, and then there are other terms that oscillate, and over an orbit, they average to nearly zero. Okay, so I'm going to go through this fairly quickly because the details are not that important. What does matter? Sorry, go ahead.
What's the value of epsilon that you're thinking of?
So strictly speaking, it should be, I'm going to be focusing on, for the astrophysical systems I'm concerned about, epsilon is the mass ratio. It's about 10 to the minus 4 to 10 to the minus 6.
So why would you be interested in corrections that are order 10 to the minus 4?
Because they're hugely important, and I'm going to describe that, why that is a little bit later in the talk. But one of the things that this includes is the back reaction of gravitational waves. But it also, if I have an effect at the 10 to the minus 4 level, and I observe a system that has 10 to the 4 orbits, that even small effects at that order integrate up and have a significant impact. I'm actually going to show you that where people are now worried about second order effects. And when you look at second order effects in this language, well, anyhow, just hold that thought. I'm going to show you a result in a couple of slides that helps to illustrate why these higher order effects are so important.
If I can add a sentence, these small numbers are so important because they are leading. They are the leading violations of conserved quantities.
That's exactly a good way to put it. Thank you, Barak. They are the leading violation of conserved quantities, and they accumulate.
That's the point. Otherwise, you don't expect to measure anything below 1% at best, eventually, including systematics and all the noise.
That's right.
So
but
I think
one of the reasons I'm going through this sort of 2 timescale analysis is it helps me to understand which effects accumulate and which do not. So these terms that oscillate, they don't accumulate. But the terms that survive an averaging procedure, they accumulate. Does that help?
that's the answer that I was looking for.
Very good. Thank you. Okay, so I put all this together, and I have a system of equations, and answering the question that was just asked here. I have terms that accumulate, which are the ones that have angle brackets around them, and terms that oscillate. One of those things just describes how, at leading order, the integrals of motion evolve. And this is when you teach a general relativity class and you learn about the quadrupole formula. That is what these terms are. Slightly different time variable, but this is, at leading order, this just gives me the quadrupole formula. I also find that there's a conservative impact on the binary. This is an effect that is small per orbit, but again, it can accumulate. Okay, so let's look at how it accumulates. So what I want to do is integrate up and see how the phase changes as I go from, let's say, T1 is the moment a system enters my band, T2 is the end of my observation. I get one term that involves just my geodesic frequencies integrated over the time frame over which my integrals of motion are evolving. I'm going to call that phi dis 1. So that's the leading order dissipative effect. If I only include that, we make what is called an adiabatic model. It's essentially a geodesic that is slowly evolving. And then I look at the next couple of terms. There's a conservative correction to the frequency that is integrated over that inspiral. And there's a term at the same order that is the geodesic frequency integrated over a correction to the duration of inspiral due to the next order in perturbation theory. They both accumulate, and they accumulate at the same order. They are much smaller than the leading term by about a factor of mass ratio, but they're not zero. They, in fact, when we do these analyses, they actually change things at a significant enough way that we're worried about them. We call them the first post-adiabatic effects. And so when we make our models, Right now, we are trying to understand how to do these things to first post-adiabatic order. So because we really understand everything at first order in perturbation theory, the dissipative thing is totally understood. We call those adiabatic waveforms. The first contribution to the post-adiabatic term, we understand how to do that. It's just expensive to calculate, and it's only been done for a handful of cases, but no issue of principle prevents us from doing it, essentially aside from access to CPUs. The last piece, and this sort of gets to one of the points you were just asking me about, it actually is a term that involves the second order self-force. So this is something that is suppressed by mass ratio squared, but because it leads to effects that accumulate, it actually has a non-negligible impact on things. This is the frontier, and its first results have recently been published. And I'll describe what those first results are in a couple minutes. I'm going to focus the next couple of minutes, for the next couple of slides rather, on just the adiabatic models. So the leading approximation is I'm just going to treat the system as a geodesic, and I'm going to allow it to flow through a sequence of geodesics due to the back reaction of gravitational waves. So the grid, what I basically do then is I lay out a grid of orbits and I solve the equations of black hole perturbation theory at every point in this grid of orbits. So my parameter space is kind of a notion of mean separation and eccentricity. At every point on the grid, I solve Tucholsky's equation and I develop a multipolar expansion of the shift to the space-time due to that small body. In this particular grid, there are 1,440 orbits, and I developed I solved the Tucholsky equation a little under 13 million times, and I've done various tests and showed that this has converged to a degree of accuracy it was good enough for our first tests. I should say that we're sort of revisiting this now, and it's not quite good enough, but that's a different story we can discuss in questions. So at every point in this parameter space, you can see what the waveform looks like at that instant. Okay, so up here at P of 10 roughly and an eccentricity of 0.6, you get that blue waveform, and it's got the sort of very sharp features associated with an eccentric orbit. Down, when I sort of get down to the lower left of this diagram, that's actually a nearly circular orbit. Okay, there's a big sort of spike difference there, and that's because it's moving at such, as seen by a distant observer, it's moving so rapidly that you're getting an effect that's akin to synchrotron beaming. I'm looking at this in the equatorial plane, and you're getting kind of a synchrotron beaming effect as that thing is coming towards you. Once I have all these data, we just need to compute how the radiation reaction evolves the system. So if I give you give me initial conditions, a grid like this gives me all the information that's needed to evolve to a final state. So here's an example. I just plopped it down at a point that I honestly just selected at random. And this inspiraled until it reached the last stable orbit, very close to the point I just drew there. Once I have all that, I can just stitch together the waveform along that sequence of snapshots. Okay, and so here is the waveform that I make in that case. This is being viewed from a different angle than the ones I showed earlier, which is why the late waveform looks a little bit more like a circular orbit. We're seeing this more from face on rather than edge on. But the point I would make is, once we have data sets like this, it's then just a matter of sort of software engineering to put these things together and to compute lots and lots of these waveforms. So here's a reference where we sort of lay out the general framework. A lot of the data for making this, we're revisiting it now, trying to make it better for sort of LISA measurement purposes, but it's publicly available. And I have some code that I share with people. It's almost publicly available. I have one module that involves proprietary software that I need to remove, and if I had time, I would. But that is happy to share with people who are interested in this. So I suggest you turn your volume down slightly, because what you get when you put this together is a gravitational wave, an inspiral that looks like this. This system is actually designed to have the characteristics of what we expect for a typical LISA source. So this is generated by my former student Steve Trasco many, many years ago. But it still holds up pretty nicely. And you can see as it proceeds, there's interesting features related to the different modulations of the frequencies. You can see it becoming more circular. When that happens, I can see Shahar taking his headphones off. Sorry about that. It's getting more rapid as it goes in the strong field. And then it was nearly circular there at the end and then rapidly plunges, and that's the end of the inspiral. So we're trying to make a giant array of systems like this. One thing that we have learned really helps is that these waveforms are complicated. You saw in that sort of inspiral there that you have this very complicated structure associated with all the different modulations that are going on. And although that is true, the overall waveform has a very complicated structure thanks to all the different wiggles. You can think of it as a sum of what we call voices, essentially the different harmonics and multiples that go into it that are themselves individually quite simple. So you have a complicated sum of many simple, well-behaved summands. So here's an example of what the amplitude and phase of some of the most important voices in that waveform looks like. So all of the phases that contribute to this have a shape that is just a harmonic of the plots that are in the upper right here. And the various amplitudes that contribute to that sum, they all look similar to what is down on the lower left. And the thing which I want to call attention to is there is variation there, but it varies on a much slower time scale than the waveform itself does. So that means that if we just compute what the inspirals look like, we can sample the data for the waveform voices very sparsely and construct the waveform with good interpolation techniques. This is the
question about the previous slide.
Yes.
Out of curiosity, what's the difference between the two graphs? Namely, isn't it plotting on the y-axis, isn't it the amplitude in both cases?
So on the top axis, sorry, the top axis is, sorry, the top plot is showing the accumulated phase as a function of time. So phi 100, that is the phase associated with axial motion. Phi 001 is the phase associated with radial motion. And so let me go back one further slide. If you look at the, if you look at the waveform, it's sort of the amplitude e to the I that phase. Okay?
Okay, thanks.
So this, it's e to the I top plot, and then each voice is then being multiplied by things related to the lower plot.
Question?
Yes.
Have you thought about the situation, the expected situation where you get many of these events seen?
Yes. I'd like to hold that thought for a little bit later, but that is indeed, I mean, I'll address it partly now. So every one of these events is expected to last on the order of several months to several years. And over the lifetime of the LISA mission, the rate of them varies with time. Sorry, I should say the rate is that there's a wide span of predictions for how many you expect to see, but hundreds is sort of the median value. So you absolutely will have multiple ones going off at the same time. And so one of the reasons why we're doing the kind of work that I'm discussing here today is that we need to start simulating how to, how do we handle the problem of multiple events like this happening simultaneously? How do you detangle sort of the cocktail party problem of multiple voices sort of singing with these gravitational waves and detangle them from each other? I can address in questions at the end, some of the wisdom why we think this can be done, but we absolutely are, I would say, depending on who you talk to, either very excited by this problem or very terrified by this problem. Both are true. So, talking about this way that we take advantage of the smoothness of these things, this has led to a program to exploit this sort of structure to assemble waveforms very rapidly. And the key point is that you can compute and store all the data, put it offline somewhere, build interpolants that describe these various smooth data sets across the entire span of the data. You sort of find some are going to contribute more than others. You have to do a little bit of study to sort of decide which ones are more important to the time domain waveform and which are not. And then a lot of this, because it's essentially just matrix multiplication, matrix operations, you can use graphics processing units to accelerate various steps in the process. So here is that waveform that I showed you earlier. And so doing this on my laptop, sort of reading in the data, doing a brute force calculation of every non-zero harmonic, that took about 3 hours to assemble this waveform. If I follow this sort of procedure at the bullet points here to the left, I can make exactly the same waveform, but it only took 0.3 seconds. And so this sort of fast emery waveform project that has been developed to exploit these data is really been kind of a game changer. And to answer the question you were just asking me about, prior to being able to do this calculation rapidly, we were all, I would say, terrified of this. Well, at least now, I think we have some confidence that we can do many of these, we can calculate these waveforms reasonably well. And so there's a lot of excitement about the process of trying to detangle multiple events from one another. So I want to, in my last couple of minutes, I want to talk a little bit about some of the physics that shows up in these systems. So the way I generate these adiabatic systems, we calculate radiation off to infinity, as well as radiation going into the event horizon. When you study the two contributions, the infinity and down the event horizon, what you find is that the flux to infinity, I'm just going to focus on the energy flux, it always takes energy away from the binary. But the energy down the horizon actually has an ambiguous sign. If the orbit, so I just think of a particular mode that contributes to this, if the orbit is whirling around the faster, if its frequency is faster than the spin frequency of the black hole, it also acts as a sink of energy. It takes energy away from the orbit. But it actually adds energy to the orbit if the black hole is spinning faster. And this is a non-negligible effect. One of the things we find, so we did some studies looking at how much of an influence this would have. And the sort of the way I like to joke about it is, let's imagine you get into God's medicine cabinet and you flick the boundary condition on the black hole event horizon, you just turn it off. What you would find is that the amount of time that a system spends in band due to that boundary condition can change by weeks. Barak, I see you just unmuted yourself. Do you have a question?
Yes, I do. Is this a good time to ask a question about the averaging method that you presented a little earlier, or should we wait till the end?
I think I would like to wait to the end because there is a bit of a subtlety associated with that. And there's some physics that because of time concerns, I'm ignoring that's related to that. But we can have an interesting discussion about that.
I'd be happy to.
Excellent. Okay, so just in terms of this flux down the horizon, where I will emphasize that the averaging is unambiguous here, at least, at least for this problem, there's an effect where it can change in spiral by of order weeks. So it turns out, and I'm going to sort of just describe this in a very qualitative way, we can actually recast that radiation down the horizon as the tidal field of the secondary acting on the larger black hole. And another way to think about this is it's not so much energy absorbed by the black hole, but the black hole's geometry being tidally perturbed, and then thanks to its spin, possibly back reacting on the orbit. And it turns out that when you go through the equations describing this, it looks exactly like the physics of a viscous fluid interacting with a tide. So when we put together the equations describing the way a fluid body responds to a tide, a lot of the physics of what is going on, you end up heating that fluid through the action of a tide by the action of the shear viscosity. So the shear viscosity, if I have fluid lines that are flowing in some kind of a fluid and they are sheared by some kind of external mechanism, say a tide, the shear viscosity generates entropy. What does that have to do with black holes? Well, thanks to Bekenstein and Hawking, it has a lot to do with black holes. We can actually recast the dynamics of the generators of an event horizon using a language that ends up looking very, very similar. So I'm going to flip back and forth here. So this is the equation on this page. It tells me how entropy is generated when I tidally shear the flow of a fluid. The equation on the right here shows how horizon entropy is generated due to shearing of the null generators that make up an event horizon. And you notice the equations are structurally identical. And in fact, you can actually identify a term in this equation that looks just like shear viscosity. Now, it's a gravitational effect. There's no fluid actually present. And so when you actually go in and look at it, that shear viscosity just depends on the speed of light and Newton's gravitational constant. But it's sort of amazing that you get this very close analogy between the two of them. Jim Hartle did a lot of work on this in the early 1970s, thinking about this, following up some ideas that he developed with Stephen Hawking. And it turns out by using some of Jim's mathematics, we're able to analyze how the shape of a black hole is affected by an orbiting companion. So I'm going to show you a little video here, and let me just describe what you're going to see in a moment. So the little lozenge in the center here it represents the event horizon of a Kerr black hole. What I'm actually plotting is a Euclidean embedding of the curvature of that event horizon. So you should think of this as essentially a soap bubble that has been distorted such that its Euclidean curvature, such that its Gaussian curvature rather, matches that of the event horizon. The little blue dot is an orbiting body that is tidally distorting the shape of that black hole. So on this part of the orbit, this is an eccentric orbit. The orbiting body is at sufficiently large radius that it's actually gone out of the frame of the video. You can see the black hole rotating here. It's slightly flattened because it's a rotating black hole. And as this body comes in, pardon me, I want to pause it. Let me try that again. Pause it right about here. Let me try that again. There we go. So you can see that the event horizon is distorted by this thing. Now I've exaggerated the distortion in order to make it clear. It would actually be sort of smaller than this by a factor of the mass ratio. But this effect of the inspiral having a duration that depends upon that down horizon boundary condition, it's essentially what we're seeing is the back reaction of this distortion to the event horizon's geometry due to the tidal interaction with the orbiting body. So,
how far was the object from the black hole in the last picture?
So sorry, can you say that again, Svi?
How far was the object? This is about...
Oh, how far was it? It was pretty close. So this was a strong field orbit. I forget the exact parameters, but it was on the order of a horizon radius away on periapsis. So it was an eccentric orbit. And so it sort of varied from being, I think on closest approach, it was on the order of a horizon radius or two. Furthest away, it was about 8 or 10 horizon radii away.
And the mass ratio that you use here?
So the mass ratio, again, what I did was I scaled it in such a way that if I did it sort of for the realistic mass ratio, you wouldn't be able to see the effect. It's there. And sort of related to a point that was made earlier, it gives me a change to the phasing that accumulates. And so it integrates up and has an interesting effect, but you wouldn't be able to see it visually. So I magnified it by essentially, I took the effect, which is suppressed by the mass ratio, and I removed the suppression, just so that I can make a good video to demonstrate what the effect looks like visually.
Okay, I was shocked thinking that an American...
No, that's right.
Hole.
So you were correct to be shocked. It would not be as large as that, but nonetheless, effect of that sort of shape would be present. All right, so let me move forward. Everything I've been describing so far is based on this adiabatic model, and it only includes this sort of leading order term. And a major reason for this is that calculating the next terms in the sequence is very difficult. So about half of the next term in the sequence comes from first order perturbation theory. We know how to do it, it's just technically complicated. But the remainder of the effect actually comes from back reaction computed at second order in perturbation theory. In order to get second order right, you have to have first order perfect. Any small numerical error will of course enter and compound. And so it's only been recently that people have been confident enough in the solutions that they are able to really do this calculation at second order. So because of this extreme technical challenge, there's been a lot of work, but not actually many results until very recently. And so at least for the case of circular orbits in the Schwarzschild spacetime, we can now compute everything up to second order in the mass ratio of the system. And what's nice is that this is a case where we can compare with results from numerical relativity. So the plot that I'm showing you, which is from a PhysRev letter written by Barry Wardell, Adam Pound, Niels Warburton, Jeremy Miller, Leanne Durkin, and Alexandre Letique. Let me see if I get this right. So the black line that is shown here, that is a calculation from numerical relativity. The orange line is the calculation done using black hole perturbation theory. In the inset, that is only done, so in the inset, we also show what happens if you only go to first order in the mass ratio. And you can see there's a significant dephasing. Second order, when you include the second order terms, they link up perfectly, at least up until the very end where there's a separation of timescale issues and some of the calculational techniques are breaking down. And the thing which I want to emphasize is that this is a case where the mass ratio is not that small. So we're using the mass ratio as a small parameter to solve the Einstein field equations, but we're getting outstanding agreement when the mass ratio was 1/10. Further work has actually shown you can do well at a mass ratio of about 1 to 3 or 1 to 4. So this seems to empirically be suggesting that the next post-adiabatic order doesn't matter that much, at least for this configuration. And so I would caution, I mean, I think people are very excited about this. I certainly think this is a beautiful result. But it's also the simplest thing possible. It's a spherically symmetric background space-time. It's an orbit with, non-spinning black hole. There's no precessions, no additional weird structure. Is this going to hold up as the binary gets more complicated? I hope to some degree it does, but it's an open question. Nonetheless, I am very excited by the fact that we're making progress with this. Now, one thing which I think I'm going to conclude my talk at talking about is that all the models we've been talking about here are based on solving the vacuum Einstein field equations. And I like to say that this is kind of like a relativist Platonic ideal of a binary system. You're imagining that the universe consists of body number 1 and body number 2, and I guess an observer who's so far away that they have no effect, and then there's absolutely nothing else. And as Shakespeare once wrote, there are more things in binary spacetimes than are dreamt of in your philosophy. We need to do better than this. So an example of the kind of thing you might worry about is, what if there's a third body? Okay, and so my thinking on this was catalyzed by a very interesting paper by Huan Yang and Mark Casals, where they sort of imagine you put an emery in a galaxy center, and they asked, well, what would happen if there's a 10 million solar mass black hole 0.1 parsecs from that emery? What they found is that by having this sort of tidal perturber, this third body acts as a tidal perturber on the system, that squeezes the binary and exerts a force relative to the background orbits. This is, I think, related to an issue that perhaps Barak Cole and I will discuss a little bit in a few minutes. Those effects almost always average out, except when certain orbits are near a kind of low order resonance, in which case an averaging fails, and then effects due to the tidal field basically magnify, they accumulate secularly and can kind of kick the binary, drives an additional precession of the orbit, and can have an effect. Now, when this paper came out, I was like, well, that's cool, but how often are you going to have a 10 million solar mass black hole near an emery? Well, it turns out the tide from a 10 to the 7 solar mass body at 0.1 parsecs, it's identical to the tide from a 10 solar mass body at 0.001 parsecs. In other words, about 1 light day. And if we just look at our galactic center, we actually see several stars of this mass within about a light day of that massive black hole. That is probably typical of many galaxy centers. And so my conclusion from this is that we need to be ready to account for what a third body is going to do. That's going to be complicated because we don't know the parameters of these things. We're going to have to sort of model these things and have sort of an agnostic way to properly fold in what these things are doing. Another possibility, and one which I've gotten both excited and scared about over the past couple of years, is that high energy observations have uncovered a variety of systems with strikingly regular eruptive flares. So one of the first ones is a source called GSN 069. It started out as a tidal disruption event. A couple of years after that initial tidal disruption event, it started flashing in X-rays every 9 hours with great regularity. So Itai Lineal and Brian Mesker have developed a model that suggests that what's probably going on here is that the original event was the disruption of a giant star, and you are now seeing the degenerate core, the white dwarf that was at the core of that giant, orbiting, and you're seeing events every time that strikes the disk that was left from that remnant. Another example, so it's a system that's been monitored for the past 3.5 years by NICER. It again shows regular eruption events, but with a periodic variation of that regularity. So the hypothesis is that what might be going on here is that this is the case where there's an accretion disk and an orbiter, and they're both precessing due to the way in which both the disk and the orbit are misaligned from the black hole spin. Finally, there was an event that showed an outburst that was consistent with the tidal disruption in March of 2018. People, when these things happen, people learn to stare at them. And starting around July of 2022, this started showing quasi-periodic oscillations at a frequency that was consistent with circular motion near the last stable orbit. So I'm actually on the committee of this student, and when she presented this, she said, "Scott, I think we might have an emery that we're studying here." But as I've continued to monitor it, the frequency has evolved, but it has evolved in a way that is not consistent with gravitational wave emission. It is inspiraling, but it's inspiraling at the wrong rate. It is not inspiraling at the wrong rate if it is a combination of gravitational wave emission and mass transfer. So there's a hypothesis that this may be a white dwarf that is generating gravitational waves and losing some of its mass, accreting onto the larger black hole. So I'm about ready to wrap this up. What I would sort of say by way of conclusion is that I think we have the easiest version of this problem under control, but I think nature is not going to give us the easiest version of this problem. And we really need to learn how to handle many of these uncertainties. And I'm just going to take a personal moment here to note that this particular one, by the way, will be right in Lisa's band. So this is something that we're hoping is still around when Lisa launches in a couple of years. But again, pointing just to myself, I am lucky because we've done a tremendous amount in the past 10 years. We're developing new measurements that I think are going to go even deeper. We need to develop better models. We need to be prepared for a lot of physics we have not thought about too carefully yet. And as I said, I have a family member who appears to have an intrinsic ability to model extreme mass ratio inspiral systems. So I would exhort all of you, if you're interested in this field, get your students started when they are young. Thank you.
Thank you, Scott, for a wonderful talk.
Thank you. It was fun. So I'm happy to take questions. And Barak, you wanted to ask me about the averaging.
Yes, yes. So my first question is about the averaging. If you can go back to the slide with the equations of motion that were separated in action angle between averages and oscillations, or drift and oscillation.
Yes. So that is back quite a ways. So bear with me for a second here. Yeah, I think this is probably a good one to start on.
Not this one, but there was a one with angled brackets, maybe a little later.
Yes, perhaps this one?
Another one, the equations of motion. Yes, this one, I think. This one would be good for me because I see here the averages, both for the angles and for the actions. And then after that, there are the oscillations, right?
Right.
And my question is motivated by other dynamical systems that involve averaging, but obviously different systems.
Yes.
Can these terms originate from a Hamiltonian? Are there conservative sectors before averaging, at least? Can they originate from a Hamiltonian? Maybe I will complete the question and then you can answer. In cases where the equations of motion are given by a perturbed Hamiltonian, then there is a rather beautiful shortcut to computing the averaged forces. Rather than averaging the forces, one first computes the averaged Hamiltonian perturbation and then takes derivatives. So instead of computing several averages, one for each equation, it's enough to compute a single average.
Right.
And I wonder whether that could be useful here, because I'm not sure that there is any Hamiltonian that describes these perturbations.
So, one nice thing about this setup here, I'm actually going to go back one slide. Actually, you know what? No, I take it back. I'm going to stick with the slide that you put me on. So we can regard, so the DJ d lambda one, that describes a dissipative evolution of the system. So that is non-Hamiltonian because it's got dissipation as present in it. The other equation, though, that is conservative. And Anna Flanagan has actually done some work proving that when you have the conservative aspect of the self-interaction preserves the Hamiltonian nature of the system. And so what you're suggesting, this is actually, so you may find it interesting to talk with Flanagan a little bit about this, because it seems very closely related to things that he's been working on other things. So I don't know how much he's been paying attention to this lately, but he has expressed a similar point of view that if you have a Hamiltonian describing the conservative parts of the system, including the self-interaction, that it may give a more efficient route to producing how the system evolves under the influence of that conservative perturbation. The other one, because it's dissipative, it's explicitly non-Hamiltonian. But that part of it, basically it's because of the separation of timescales. There is a way to sort of split conservative from dissipative degrees of freedom.
Wonderful. That would actually indeed be interesting to me. And thank you for an expertly talk. I should have started with that. And I'll let others ask questions, but maybe I will ask additional ones later.
I did just want to make one remark. I thought you might be going in a slightly different direction with your question originally. And so the point I wanted to make...
Sorry for disappointing you.
Yeah, that's okay. No, not a disappointment at all. Your question was very interesting. But the point I wanted to make is that I kind of lied to you all when I wrote this slide. And the reason is that the term that I've written as delta F, I say it oscillates over an orbit and averages to nearly zero. That is actually false. If the frequencies, the frequencies associated with theta motion, the frequency associated with the R motion are in a low order integer resonance with one another. And so there actually is an effect that arises when you go through an inspiral. Because these frequencies evolve separately, you pass through moments where these things are near an integer resonance for a little bit. And then this averaging procedure, so the term that secularly accumulates, that I've written with angle brackets here, it gets momentarily augmented by a failure to average of the other term. And that actually is, it's one of those things that's a combination of interesting and terrifying. It's interesting because it's kind of cool, strong field physics. The reason it's slightly terrifying is that the amplitude of the effect ends up depending on an accidental phase parameter. It depends on what the orientation of the geometry of the system at the moment that you enter this sort of near integer resonance.
Oh, fascinating. So there are jumps whenever resonances form.
Exactly.
But these jumps are somewhat random. You cannot quite anticipate maybe their magnitude, but not their direction, so to speak.
So to speak, that's right. That's right. And you can anticipate when they're going to happen, but you don't necessarily know how large they will be, or in what direction. Does it augment the energy flux or does it decrease the energy flux? Yeah.
Oh, beautiful.
So your question allowed me. That was a slide that I sacrificed for time, and so I appreciate you giving me that opportunity. I think I also saw Tzvi raising his hand. Is that correct?
Yeah. I understand that all the things that you're discussing are happening when in the average, the stars are around 30 or less gravitational radii
Yes.
from the black hole. Otherwise, the effects are really too small.
Right.
And recently, there was an interesting paper by Pao Amaro Swan, and they speculate. I'm not sure that they are correct, but if correct, it is a very interesting stellar dynamic issue. That there may be several stars simultaneously in such a small radius.
Yes.
And then they actually calculate the waveform from such a thing, from such a configuration, actually focusing on a three-body system, the black hole and the two other stars. And every once in a while there is a jump in the phase, which is due to this when the two stars are getting relatively close to each other. And this if this is correct, if their estimate that there will be more than one star in this range of 30 RG, then life will be significantly more complicated for deciphering
Well put. Yes.
the waveforms that come from
Yes.
memories. So right now, our own galactic center don't show anything so close, but I understand from the people in Munich, from Genzel's group, that they are getting closer. So there may be some. So if this is true, then things will be very exciting and complicated at the same time.
You know, that's, I think what you just said gets to this dichotomy of interesting and terrifying that I've mentioned more than once here. I mean, I completely agree with you. As it happens, next week I'm going to there's a meeting at the Jet Propulsion Laboratory of people who are sort of trying to get ready to do LISA data analysis. And Pau is organizing a session that I'm speaking in, so I may follow up with him about this. What I would sort of note is that both the kind of thing that I think Pau is talking about and also this possibility that some of these sources may be interacting with an accretion disk, it seems likely to me that they may be rare in the population of the sources that we're measuring, although that modeling needs to be done to pin that down. But even if they are rare, they are probably disproportionately interesting. And so they are likely to be the ones that, even if they are only a small percentage of the sources that eventual LISA measurements track, they are the ones I think we're likely to get some of the most interesting science out of. And so being prepared to analyze these things and to make accurate strong field models. So I did not talk yet in this talk about the data analysis problem. One reason why we have to make these precise models is that the extreme mass ratio waveforms are very low amplitude. And so they are lower than other sources that are going to be on simultaneously. They'll actually be lower than the mean noise level, but because they accumulate secularly, they can be integrated up above the noise. And so we do need to have good models generating where they're going, but they also need to be robust enough that we don't miss systems because we don't get the, we overlook some aspect of the physics. So, the kind of thing that you're describing to me, I think is a great example of one that's, well, if nothing else, I was just thinking to myself, this might be a fun project for a student to do some work on to try to understand, how we can put some of these additional body effects into the models that we're making. We have roughly 10 years until LISA is supposed to launch, and I hope 10 years is enough, but it's going to be a challenge, I think, to work out some of this physics.
Unfortunately, knowing how space missions operate, you most likely have more than 10 years. So
good point. Good point.
Should not be a major concern.
That's a very good point.
10 years is the minimum.
Yeah, exactly. 10 years is that's the lower bound.
ESA will give it to you.
I guess the real issue is, whether I will still be capable of participating when it launches, or I'll be too decrepit at that point.
Well, this will be a new reason for ESA for the delay, because the theorists are not ready yet. So we decided to postpone the launch for 2 years.
There you go. There you go. It looks like
All right,
Barak.
Yes.
Yes. So I missed a couple of basic points, and I would appreciate a clarification. The first was the fast Emery slide, where you explained that there was some idea that enabled an economization from 3 hours computation to 0.3 seconds. What was the mechanism? Is it this separation of modes of the motion into modes that separate separately in some approximation, or was it something else? That's one question. And the second one, you mentioned the post-adiabatic limit, but I missed what was the adiabatic limit itself.
Okay, so those are, let me do the adiabatic limit first, because that actually is what sets up the fast Emery waveform. So the adiabatic limit is the case where you are only including, you're treating the background motion of as a geodesic of the space-time, and you're allowing the geodesic to evolve due to the back reaction of gravitational wave emission. That's the adiabatic limit.
In other words, that's the first correction to the geodesic?
Exactly. That's the first correction to the geodesic limit.
And then when you talk about post-adiabatic, you're actually going to some second order?
So there's two terms that impact the post-adiabatic limit. One of them relates to your earlier question, my answer to your earlier question about whether the effects are Hamiltonian or not. And so if...
Oh, the oscillations.
Exactly. So there's an aspect so the oscillations tend to those are always subdominant, but there's an impact on the rate at which the angles accumulate that is secular, and that can be described as Hamiltonian, but it ends up being suppressed by an order of the mass ratio.
Oh, so
That's
maybe
what I
in
called
quantum mechanics that this adiabatic limit is known as the secular limit, maybe.
Yeah, I guess you could call it that. And so the term which on this slide I've called phi cons 1, that is the conservative, it's sort of a conservative change to the Hamiltonian from the self-interaction at linear order in the mass ratio. Then the next term is what I've called phi dis 2. That is second order in perturbation theory, but a dissipative effect. And it turns out that when you integrate over and you look at what accumulates secularly, they contribute at the same order.
This second order effect can include two kinds of terms. One of them is from second order cell force.
The issue here
the
is
other one
exactly
is
this.
from averaging a square of the first force, cell force oscillation squared.
That's right.
So both of them.
That's right. So they both contribute. They are less important than the leading secular term by a factor of order of the mass ratio, but they are not. It's smaller, but it's not negligible.
Okay,
Okay?
great.
And so when you do post-adiabatic, you include both of those.
Thanks.
And so then your question about what is the trick with the fast?
Yes.
So this is just ordinarily. So there's an anecdote associated with this. So I gave a presentation that essentially boils down to showing the first calculation of what is on this slide at a workshop of the community who works in this field about 2 years before COVID lockdown. And so I sort of showed how to take data that was on a grid like this, how to assemble it. And I've sort of left out a detail here, which is I should have showed that you can make the waveform in the frequency domain as well as in the time domain, which is useful for data analysis purposes. And I called it at the time, I sort of pointed out that computing these 13 million harmonics, that takes a few hundred or a few thousand CPU hours, but it's very parallelizable, and you can just store it and then use it later. And so I made the point that once you have done that calculation, you can make this waveform in of order hours using the naive calculation, which in the time domain follows every individual wiggle of the waveform. You have to resolve that structure on sort of an orbital time scale. And
but you have to prepare a bank of all possible waveforms beforehand, or just one bank of one waveform?
Well, that's kind of what we're working out right now. So what we have available are the data, and then we're trying to figure out what's the most efficient way to provide the waveforms for doing this kind of an analysis. And so when it looked like it was going to take hours per waveform, our thought was, okay, well, maybe what we ought to do is just pre-compute several. We could parallelize this. Imagine we sort of send off to a parallel cluster, 10,000 runs, each one takes an hour or two, and we get 10,000 waveforms. So I gave my talk, and the person, Alvin Chua, who is listed here, he was in the audience. So by the way, the title of my talk was Fairly Fast Emory Waveforms. And he came down and said, how about we get rid of the fairly and we just make them fast? And I was like, well, how the hell are you going to do that? And then he sat down and he's like, look, all of your data is smooth. We can just do some interpolations. You don't need to follow every wiggle of these things. We can just sort of build what the inspirals look like. We can store the data along the inspiral path. And then we can do the interpolation. We can make the waveform on the fly as we need them without needing to actually compute 10,000 waveforms at once. We can just do, say, a few hundred inspirals, store them, and then generate the waveforms as needed. And that ended up being what led to this thing that we call the fast Emory waveform.
Thank you.
I would say that this is, I often use that because, people sometimes say, well, do you really need to go to meetings? And that is a conversation that would not have happened if we were not in person together, I think. And it ended up being, there is now, if you search for fast memory waveform, the group of us who are developing these things, we were able to rapidly put together 4 or 5 papers on this thing, and it's accumulating citations faster than anything I've ever done. So on some kind of a mercenary scale, I would say that's a good example of where conversation was useful.
Perfect.
Right. Are there any more questions? If not, let's thank Scott again for a great talk.
Thank you, everyone,
Thanks
for
a
the
lot.
invitation. For those of you who stuck around to the bitter end.
I'll close the recording.